Final part of alkenes is looking at mechanisms. There are 3 mechanisms you need to learn, and you need to be able to draw them out. A mechanism is when a reaction is broken down into its parts, and it shows where the electrons are moving from and to. To show the movement of a pair of electrons, you would draw a curly arrow with a full head. That shows that electrons are moving from this end to the end the arrow's pointing to. If this was a bond, remember a covalent bond is a shared pair of electrons, then that would show a bond breaking up and both electrons going onto an atom. And that is heterolytic fission. So let's look at the addition of hydrogen halides. You can see ethene and hydrogen bromide, and you can see that the hydrogen bromide is polar. The hydrogen has a slightly positive charge on it, and this makes it electrophilic. This is where the electrophile comes from. The electrophile does not have to be a positive ion. It can be a partially positive part of a molecule. So what we say is the electrophile attacks the double bond, and what actually is happening is that a pair of electrons from the double bond move onto the hydrogen. So that double bond breaks and a pair of electrons moves onto the hydrogen. It looks kind of like a half arrow there. I'm just going to make it a full arrow. The electrons that move are the pi electrons. If you think back to when we did hybridization, the electrons in the pi orbitals, they overlap sideways. So that pi bond is weaker. So it's the pi electrons, it's the pi bond that breaks and the pi electrons that move onto that hydrogen. So that arrow shows that there's going to be a bond forming between the hydrogen and one of those carbons in the alkene. Now at the same time, you've got the hydrogen bromide molecule breaking up. Both electrons from the bond move on to the bromine atom, which means you're going to get a bromide ion formed. So we now have 2 species formed. We have our bromide ion, and we have this species known as a carbocation. And if you remember, carbocation is a species, a molecule, which has a positively charged carbon. That carbon is now electron deficient. And we can see the bond that has formed between one of the carbons and the hydrogen from the hydrogen bromide. And we can see that what happens now is that the bromide ion is attracted to the positive carbon, and a pair of electrons from the bromide ion moves onto that carbon, and you will get a bond forming. So that is the mechanism that you need to be able to draw. You need to be able to show the arrows, show the electrons moving. Hydrogen halides always react with alkenes via a carbocation intermediate. The next mechanism is for the acid-catalyzed addition of water. This is quite similar to the one we've just seen, in that you will get a carbocation intermediate forming. So we have ethene again, and this time we have the hydronium ion. And what has happened here is water has reacted with the hydrogen ion. Remember, we say this is an acid-catalyzed reaction. So the hydrogen ions have reacted with water molecules to form the hydronium ion. And that means that hydronium ion has now got a positive charge, and that is our electrophile. So our electrophile in this case is the hydronium ion. And we say it attacks the carbon-to-carbon double bond. Although we can see what is really happening is, once again, the pi electrons from the carbon-to-carbon double bond are forming a bond with a hydrogen. At the same time, or once that happens, you can see that two of the electrons from the bond that was between oxygen and hydrogen move onto the oxygen atom. So you will reform water. You'll reform water with its lone pairs. So here's our carbocation intermediate. You can see in green the bond that is formed between the carbon and the hydrogen from the hydronium ion. You can see that the carbocation intermediate, as you would expect, has a positive charge on it. And what happens now is that water now uses one of its lone pairs to form a bond with the positive carbon. And we get an alcohol formed. And what also happens is a lone pair will go onto the oxygen, and you will get your hydrogen ion regenerated. So it's a catalyst. Now we can use carbocations to explain Markovnikov's rule. Remember, Markovnikov's rule predicted which would be the major product and the minor product of addition. So we need to know a bit about carbocations. Well, carbocations can be tertiary if the positive carbon is attached to 3 alkyl groups, secondary if the positive carbon's attached to 2 alkyl groups, primary if the positive carbon's attached to 1 alkyl group, and you can also get a methyl carbocation, which we class as primary. Now, these have different stabilities. The most stable carbocation is the tertiary one, and then they become less and less stable. Why is this? Well, the presence of alkyl groups, so I'll show you what I mean by an alkyl group, 1, 2, 3, they're full of electrons, and they help to stabilise the positive charge on the carbon atom. We say that alkyl groups are electron donating. So the presence of those electrons close to that positive charge just helps to stabilise the carbocation. So the more alkyl groups you've got on a carbocation, the more stable the carbocation is. So let's look at this example here. Up at the top left, we've got our alkene reacting with water. And Markovnikov's rule says that the hydrogen will go onto the carbon that already has the most hydrogens, which is that one in yellow. And you can see there that that forms propan-2-ol. And if you look down below, we can see why. When the hydrogen goes onto here, you get left with the positive carbon on the middle carbon. So you form this secondary carbocation. And that's more stable than if the hydrogen was to go on to the middle carbon and leave the end carbon positive. So because to form propan-2-ol we go via a secondary carbocation, And to form propan 1-ol, we go via a primary carbocation. The major product is the propan 2-ol, because the secondary carbocation is much more stable than the primary one. Final mechanism, addition of a halogen. So this is like adding bromine across a double bond. Now this is a little bit different to the last two, and it's a little bit more complicated. Here we have ethene and bromine. Now looking at that, you should see that something looks not quite right. Bromine bond should be polar. No, sorry, should be non-polar. Okay, they've got bromine joined to bromine, so it should be non-polar. But you can see that one of the bromine atoms has a slightly positive charge and one has a slightly negative charge. So why is this? Well, bromine molecule is non-polar, but as it approaches the electron-rich carbon-to-carbon double bond, a dipole is induced in the bromine molecule. So as it approaches that negative double bond, the electrons in the bromine molecule are repelled towards the opposite end of the bromine. So what we say is that there's been an induced dipole in the bromine molecule. And because of that, we now have an electrophilic part of the bromine molecule, which will be attracted to the electron-rich carbon-to-carbon double bond. In this case, the electrophile is the end of the bromine molecule that is slightly positive. As before, the pi electrons from the double bond will form a covalent bond with the bromine. At the same time, the bromine molecule breaks up by both electrons going from the covalent bond onto a bromine atom. And you get this rather interesting looking species. It's not a carbocation, we call it a cyclic ion intermediate, because you can see that the bromine has formed a cyclic structure with the two carbons. So what's happened? Well, if we look at the green arrow, we can see that that is responsible for forming a bond from the carbon to the bromine. This bond is a result of that bromine donating one of its lone pairs to form another bond with a carbon. Overall, that ion has got a positive charge. It's electron deficient. So what happens now is our bromide ion comes in and it donates a pair of its electrons to form a bond with that carbon. And the bond that you can see there in pink, both of those electrons move on to the bromine. So what we get is this molecule. It's got two bromines on it. We can see the original bond between the carbon and bromine in green. And we can see the bond formed between the carbon and the bromine when the bromide ion came in. And that says, actually, it says bromine. It should say bromide ion. So this is a little bit of a different mechanism that you need to learn. You need to be able to draw all the arrows in, and that just takes quite a lot of practice.